Hello there. In this video, I want to talk about multiplying binomials when there are radicals involved. So this kind of picks up with the idea of the adding and subtracting radicals video. How do we extend that to multiplication? Or you could look at it as when we're multiplying binomials with different terms, how do we extend that beyond variables into radicals? So the process does not change. If you were fond of the table method, which I'm going to use, you may. If you're more fond of double distribution, go ahead and give it a chance now. I'm going to go ahead and use my table method. So I know that square root of 2 and square root of 3, actually, sorry, negative square root of 3 is at top. And I can't remember if I said this in that video, but it doesn't matter if this 2 minus square root of 2 minus square root of 3 goes on top or on the side. You should get the same answers. Now, square root of 4 I know to be 2, so I'm going to simplify that first. I'm going to write 2 here, and then square root of 6, that doesn't simplify. And that's actually something I should point out. When we're doing this, we should simplify before we throw it in, because if we don't, we will probably need to simplify. In fact, we definitely will, and it'll make it more complicated. So we've got 2 times the square root of 2. Well, that's just 2 square root of 2. 2 times the negative square root of 3, so that's negative 2 square root of 3. We've got square root of 6 times square root of 2. That's square root of 12. All right. Now, I left myself a little bit of room. Let's simplify that. Let's simplify that in the margin here. So 12 is 4 and 3, and then this is 2 and 2. So this is equal to 2 square root of 3. Oh, interesting. Interesting. And then we get 6 times 3. That's a negative square root of 18. Let's go ahead and simplify that. So 18 is 9 and 2, and then 9 is 3 and 3, and we got 3, or negative 3 root 2. Now, we can go ahead and do our adding of diagonals. So this is nice because these end up being like terms. When you're multiplying binomials like this with radicals, it won't always work out this way. You could end up having 4 distinct terms with no like terms, and in which case you'd have a 4-term answer. It's possible. So, but this is 2 root 3 plus its opposite. This is just equal to 0. And then here you have 2 root 2 minus 3 root 2, which would just be 2 minus 3, which is just negative 1. So this final answer would be negative root 2. Let's talk about another example. So now we're getting into cubes. So this ought to be interesting. So again, I'll set up my area table. So I got cube root of 14, negative cube root of 7. Okay, you're going to have to know some multiplication facts for this one. Don't go reaching for the calculator. Let's challenge ourselves to do this mentally. So cube root of 49. And then we've got cube root of 4. Okay. Nothing to simplify, so we go right into the multiplication. So we've got, okay, cube roots will ultimately be in all these squares. So we got cube root of 49 times cube root of 14. Well, I know that 49 is 7 times 7, and I know that 14 is 7 times 2. So I'm just writing out the process that would go in my head. Well, this is 7 cubed right here, so that's 343 times 2. Well, we just double all these numbers, so that's 686. But at the same time, I've got a pair of 7s the same way that if I had created a factor tree, oh, sorry. Maybe I just shouldn't talk and write at the same time. Multitasking is too hard. So we got 7, 49, and 7, and 7. So if I created a factor tree for this, I would get that same triple pairing. So what I'm going to do is I'm going to put my 7 on the outside, and then I've got the cube root of 2 remaining. Okay. Now we've got 49 times 7. Well, we've already established that's 343. So cube root of 343, and it's going to be a negative, is just negative 7. So that's beautiful. We got 4 times 14. Well, that's 56. We could set this up the same way we did 49 and 14, but since I know it's 56, I'll break down my factor tree. That's 8 and 7. That's 4 and 2. And that's 2 and 2, so I get a pair of 2s. And then I've got the 2 and the 7. So what I ultimately led with is it's a cube root, so I'm looking for triplets. So 2 cube root of 7. So I actually kind of got the opposite, or the flip, of the top left square. And then we got 4 times 7, that's 28. And really quickly, just to demonstrate here, 28, 4 and 7, we know that already, 2 and 2. There's no threes. There's no 3 of a kind, I should say. So this is just cube root of 28. And this is kind of what I was talking about in the previous example. It was kind of nice that it worked out to such a simple answer, because now we can see we've got 4 terms all with different numbers in our cube root, and then this one without a cube root at all. So our final answer is just going to be 4 distinct terms. So how you write it out is up to you. I'm just going to work top to bottom, or left to right, top to bottom. Okay, so I'm going to do 7 cube root of 2 minus 7, and then we got plus 2 cube root of 7, and then plus cube root of 28. So yeah, that looks kind of funky. It probably would have been better if we just left it in its original form, but at the same time, we got some good mental math exercises out of it. All right, so let's talk about square root of 12 plus square root of 24 times the square root of 18 minus square root of 54. So again, probably be best if we simplify this first. 12, we know from earlier, ends up being the 2 square root of 3, okay? So we get a pair of 2's and a 3 out of it. 24, so let's do 24. I don't think we've done that in this video. We've done it in other videos. I'm actually going to do it in a different color because there's a lot of blue on the screen right now. So we've got 2 root 3, 2 root 6 at the top. That's for this first term, okay? And then we've got 3 root 2, and then negative 3 root 6 at the bottom. So let's see what comes out of this. So we've got 3 times 2, that's 6, and then another 2 times 3, so that's 6 root 6. Okay. Then we got 2 times 3, that's 6. But I see that if I get 2 times 6, that's 12. Okay. So let me write this down. So 3 times 2 is 6, but 2 times 6 is 12, and that comes back to this original. We know that is 2 root 3. So times 2 root 3, which is just 12 root 3. Okay, now we got a negative 3 times 2. That's a negative 6. Ooh, looking promising with the negatives. And then 6 times 3 is 18. Well, we know 18 to be 3 root 2. So times 3 root 2. That's negative 18 root 2. And then we've got negative 3 times negative 2 is negative 6. But then we get that 6 times 6 is 36. But that's inside a radical. We know the square root of 36 is 6. So we end up getting negative 36 overall there. Now, I want to pause here for a second to mention that when we do this with variables, generally the way it works out is the diagonals add together. As we've seen in this video, it may not work out that way. We may get 4 distinct terms. That's what happened on the last problem, and it looks like that's what's going to happen on this problem. I will also take the time to point out that depending on what your radicals are, you may not end up with diagonals adding together. You could end up with a column adding together or a row adding up together. So I just wanted to take time to point that out. So final answer, 6 root 6 plus 12 root 3 minus 18 root 2 minus 36, and nothing combines, so that is our answer. Last example, now we've got negatives. So let's go ahead and set up. So I'm going to use purple now. Square root of -3, and then square root of -5. And then we got square root of -3. And then we got minus square root of -5. Okay, great. Okay, so we got a -3 times a -3 within the square roots. And that would be square root of 9, which that'll just give me 3. Okay. Then we got a -3 times a -5, so that's square root of 15. And that's just two prime numbers multiplied together, so that can't simplify. You got another -5 times -3, so that's negative square root of 15, though, because we have this negative here. And then we got -5 times -5, that's 25. Square root of 25 is 5. And it looks like we got the diagonals adding nicely together, with this being equal to 0, and then this being equal to 8. And so our final answer is 8. Go ahead and give a like and subscribe. And if you want to see other videos in the future, go ahead and leave those in the comments. Thanks for watching. Okay, I couldn't leave you hanging on that note. I wanted to let you know that this is not correct. You might have already left a comment in the comment section saying this is incorrect, and that's perfectly okay, but I set you up, I admit it. So let's talk about this problem in general. Let me go ahead and erase this since it's wrong. Let's go ahead. Remember the rule of multiplying radicals together. So this idea that square root of a times square root of b equals the square root of a times b only applies to positive integers, okay? All of these are negative, which means we're going to have to go to the complex world for this. So we're going to need to simplify. When we see a negative under the radical, we're going to rewrite it as, I always like to write my complex imaginary number I out front. So I root 3 plus I root 5 times, and then same thing here, I root 3 minus I root 5. All right, great. Now we can set up our table. I root 3 times, or no, not times, just column, I root 5. And now we get a good look into this property over here. Why does it only work for positive integers? I root 3 and I root, or sorry, negative I root 5. Well, let's get our answer and take a look at why. So we've got the 3 times 3, which is 9. And if we take the square root of 9, that definitely gives us 3. But also notice we get the I times I. I times I, so that's I times I is I squared, which is -1 based on the definition of an imaginary number. So we get an extra negative out in front. And right off the bat, we can see why. Square root of -3 times square root of -3 is meant to cancel out the square roots, because that's the square root of -3 squared, which just leaves us with the -3. That's what we're supposed to get out of it. If we apply this property where we're combining them together, we got +3, and it didn't work out to be the same way. But based on what a square root is, you're undoing the process of multiplying something by itself. You get the negative. Okay, so let's continue. We got 3 times 5, that's 15, but then we got the I times I, so this is negative square root of 15. So you may notice our square roots end up being more or less the same. We just didn't have negatives. Or in this case, we got 5 times 3 is 15. So we still get the square root of 15. But now we got an I times I, which gives us -1, but we also have the additional negative. So this just can remain positive. And then we've got the 5 times 5, which is 25. Square root of 25 is 5. And then we got the negative I times the I, which gives us -1, or rather negative of a -1. So this gives us +5. So again, let me rephrase that because I don't think I said that clearly. So we got that negative I times I. Well, this gives us negative I squared. which gives us a negative of a negative 1, which just gives us 1. So the 5 is positive as well. So when we add these together, this diagonal still nicely comes out to 0, which is a relief. But then we get a negative 3 plus a 5. So our answer, should actually be 2. But I've already done the sign-off line. Thanks for watching.